morning, good afternoon, everyone. My name is Tom van Ekelen. I will be one of three presenters during this joint ToolCraft Siemens webinar. During this webinar, we will show our end-to-end workflow. And after this presentation, you will have the opportunity to ask questions. During the presentation, our cameras will be switched off. The title of the presentation is From Design to 3D Printing, the Value of an End-to-End Workflow. And I will start with the agenda. So we will first have an introduction of ToolCraft. This introduction will be given by Kevin. Then we have a presentation on the added value of the entire process chain and the first preparation of build plate, or the first build plate in our workflow. This will be done by Mike. Then I will present the process simulation and the compensation workflow. Then there is a second preparation of the build plate as it will be sent to the printer. That will be, again, done by Mike. The actual printing and post-processing will be shown by Kevin, so the work that has been done here at ToolCraft. And then the final part of the presentation will be scans and comparison, so the scan of the printed part and the comparison with the nominal geometry, which will I do again. And then there will be conclusions and questions that can be asked. So we will go now to Kevin. So Kevin.
Thanks. I will just start with a quick introduction to ToolCraft. ToolCraft was founded in 1989 based near Nuremberg, Germany. ToolCraft has a wide range of applications such as additive manufacturing, robotics, machining, injection molding, and mold making. Since 2011, we are a supplier for high-end additive manufacturing components, and we have around about 10 laser powder bed fusion machines, 3 DED devices, and around about 50 multi-axis milling centers. 2019, we created a new brand. It's called Ambitious. We are also a Siemens solution partner, and we are a team of 9 members. We provide at Ambitious consulting and training around additive manufacturing in general. We offer very high quality training in design for additive manufacturing. We do also the technical support for our customer. ToolCraft as a manufacturing wide range of applications like semiconductor, medical technology, automotive, vehicle technology, and motorsports. Also aerospace and security. We are special machinery manufacturing and a lot of other stuffs. As ToolCraft, we are certificated with a high quality in DIN ISO 9001, also with a medical certification, with the NetCap for welding and for non-destructive testing.
Thank you, Kevin. And we go to Mark.
Using Siemens NX as an end-to-end solution for additive manufacturing offers 5 significant advantages. Advantage number 1, integrated workflow. NX provides a unified platform that consolidates the various stages of additive manufacturing workflow. This unified platform eliminates the delays and inefficiencies associated with transferring data between different software tools for customers like ToolCraft. Advantage number 2, associativity. The associative process in NX ensures that all stages of the workflow are seamlessly integrated. Changes made by Kevin at any stages of the design process automatically propagates throughout the entire workflow. This guarantees data consistency and reduces the risk of errors that might occur due to manual update. Advantage number 3, enhanced simulation and validation. NX includes robust simulation tools that allow for the analysis and optimization of designs before printing, as Tom will present later. Advantage number 4, efficient build preparation. NXAM offers comprehensive build preparation features for scaling up production. For example, we can aggregate existing build preparation data into new builds without data duplication. Another example is having a dedicated build processor server, centralizing all output generation on a single machine. Another set of features that is relevant for scaling up additive manufacturing is providing direct integration with all major OEMs, including TRUMPF. This set of tools ensures that parts are prepared efficiently for printing, scaling production from 10 to 10,000 parts without compromising on performance. And advantage number 5, automation. NX API allows companies as Toolcraft to scale their additive requirements to leverage expert use cases that enable business transformation at Toolcraft and other customers. Next, let's have a look at a sample end-to-end workflow from design to 3D printing. We'll start with an aerospace part derived from brake manifold for Airbus A320, printed with titanium 60 microns. So we'll start within NX modeling. We'll run part orientation optimizer. We'll try to orient based on minimum support volume, but we cannot balance based on print time estimation and overheating. We can start the calculation based on multiple criteria. We'll get a weight result. Based on that result, we can create a print coordinate system that we can use to orient the view within the modeling based on the print view. And we can switch to NX additive manufacturing application. At this stage, we select a new TRUMPF 5000 printer. We generate support structures based on the best practices created by Toolcraft. We have automatic supports. We run slice area distribution with an accuracy for 5 millimeter. We can go as low as you want. We can go even to 10 microns. We get a slice graph oriented in the view automatically based on PMI nodes. And at this phase, we prepare the first stage of the build preparation workflow.
Thank you, Mike. Then the next step is simulation. So we will simulate in order to compensate for the printer deformations, the geometry. And to do the simulation method that we use is so-called inherent strain values. So the first step that we have to do is a calibration. And that means that we have to print the calibration beam set that you see here at the top. So you do that on the printer, you do a cut, then you measure the displacements, and from that you back calculate the inherent strain values. And you see that in the menu on the right. So for a given material printer, you have the inherent strain values that goes for that process. Now, then in this webinar, we actually compensated 2 parts. So we did 2 compensation simulation. And the reason for that is that we have the inherent strain value for the specimen, but for the support structure, we also need to obtain mechanical properties. And these mechanical properties, we derive them from the specimen properties, and we calculate so-called volume fraction of the support structure. So the support structures are faceted support structures. They do not fully fill a voxel. So for the voxel, we calculate a volume fraction, and then with this volume fraction, we scale the mechanical properties. Now, there are multiple ways of doing it. And so we have 2 configurations here, configuration A and configuration B. So where we scale differently, we obtain a different stiffness value for the supports based on the volume fraction. And we printed those 2 parts so that we could actually make a decision which type of scaling is actually better. Then to do the actual simulation, once we have done the calibration, these process parameters are saved in a database. So then to do the simulation, we just have to choose this calibration parameter set and do the meshing and then launch the simulation. So here we start in NXAM, where we have the part and we switch to the PBF solution, the voxel-based solution. In the ribbon bar powder bed fusion, you have to go from left to right. So the first thing we do is we select the TruePrint 5000 titanium data set. Then we do the voxel meshing. We do 1 millimeter voxels in this case, the same as what we do in the calibration. The voxel mesh will be generated. So we have the mesh for the solid, and then we have the blue mesh for the support structures. And this blue mesh will have a varying volume fraction, and so we have different properties. Here we do have an estimation functionality to fit your simulation onto your machine, so with an optimal number of processes, memory, depending on the size of the model and depending on the machine that you are using. So you can modify these values, but it helps you to really set up the problem. Then we solve the problem, so automatically the entire model is created, all the loads and boundary conditions, the inherent strain values are applied, the material properties are assigned. The calculation is launched automatically. Normally, the calculation is launched on your machine. In this case, we can also launch on a remote machine, so on a remote Linux machine, for example. Then once the simulation has been done, you see the results on the voxels. You can step through the different subcases. You can also step through all the layers. We have an animation that will show the actual build-up process taking place. And then we have two different types of visualization. One is where we visualize the results on the geometry, including the faceted support structure. This is what you will see next. And so you will see that here. So you have it visualized on the geometry and including the faceted support. And the last type of visualization is more like a deviation gauge, where you have the variation or the deviation from nominal geometry. So the values now are from minus to plus, and we can do that for the different cases. So after printing, after support removal. And then the final step that we will do here is the compensation. So you select when. We apply here -1 as a deformation field. And you can also determine what the resolution is of your compensated STL files. So we create these compensated STL files of the part and also of the support structures. So the part will be deformed, but also the support structures will be deformed to match the deformed part. Now, these are just files that have been exported. So then we go to the next step, and we're going to create a build plate with the compensated part and the compensated support structure. So the first thing that we do, we open a new model. And, well, we give it a name that goes with it. Then we import the STL file, and we import the STL of the deformed part. And we import it as a convergent so that it is converted into a solid. So now we have a convergent model in this part. We save it, and we go to the build plate. And here in the build plate, we load the part file. And then the convergent is put in the right position on the build plate. Then the next step is in the modeling application, we load now the STL files of the deformed support structure. So there is a solid support structure, and there will be the faceted support structures. And these are deformed, pre-deformed or compensated just like the part. So they fit directly, so you don't have to regenerate the support structures. Then we go back to the additive manufacturing application and apply them as user-defined support. So this is the last step. And now we have a compensated build plate with the user-defined support. And this could be either re-simulated or be sent directly to the printer. And so now I will hand it over back to Mike, who will show the next step.
Okay, the next step, it will be to continue our workflow within an NX additive manufacturing application. Let's add within a new TrueTop Sprint 5000 build tray, the three independent parts together with their supports. So this is the stage where we have multiple parts with their supports within the same build tray. Let's run rebuild validation steps where for a part selection or for all the parts at the same time, we can check for non-manifold bodies, we can check for deviation gauge, and we can check for collisions. This build inspection we can do for a subset of parts or for all the parts. At the same time, we get back the maximum deviation and the minimum deviation when comparing the output mesh with the nominal geometry. This is an additional step that will provide the confidence that the output it is conformal with the nominal geometry. The next step, it will be to select one of the available TRUMPF build strategies. We select titanium, and XAM will automatically retrieve those build strategies from the TrueTop Sprint application, and we will generate the output on the build processor server. From within NX, we can check the printing progress on the server in real time. The print server can be shared between multiple users. So we'll have a server on a central location that is shared between multiple users within the same enterprise that will be responsible for generating the output in a central location. And the user will get in real time the progress of the printing of any possible error messages coming from the printer. When the print job is finished, we have the possibility to download the output from the build processor server on the local machine, and we can run the validation and verification directly within an XAM application. We can use the path viewer to load the layer stack. Within NX, we can scroll back and forth between all the layers available within the output file. And for one of multiple layers, we can generate a preview of the vectors for that specific layer. We can zoom in, and we can actually see the individual vectors and their directions, both for the solid part geometry and for the non-solid supports in this case. We can scroll back and forth, jump back and forth between different layers, and we can scroll back and forth between the different sequences and different vectors at a given layer. Of course, the most interesting layers are the most relevant for looking at in detail for the vector, the path vectors, but all the data it is available within NX. Once the path verification and validation is done, we can also open the output file, WZ file, within the OEM software and to run the similar type of validation and verification that we just done within an XAM context. We can scroll back and forth between the layers, and we can zoom in at any given layers and zoom in detail and see both the vectors and their direction. At the end of the process, we can generate a report of the current setup. It contains information as build density, maximum and minimum Z height, a cost estimation, and a print time estimation. The cost estimation, we can do this for each, for the material component and for the machine component. Last but not least, we also have an associative process. That means if we go back within the development phase and add a design change, in this case, by scaling the initial body with an uniform scale factor,
So then we go to the next part of the presentation, which is will be given by Kevin.
Thanks, Tom. I will just give a quick introduction to the process circle at ToolCraft. In the next slide, you will see a video, and I will just guide you through. After the build job preparation shown from Mike, it all starts with printing. After printing, we have to unpack the components. You will see it in a few moments. And also, we have to remove the powder. After the powder removal, visual inspection is done if there are any errors occur. First, quality assurance is done with the GOM scan. After this step, we go to a wire EDM machine, cut off the build plate, and releases the parts and the supports. The supports were removed by a new developed technology you will see in the video. After support removal and grinding the support surface, we will refinish the functional features and surfaces. And after all of that, in House of ToolCraft, we have a final quality assurance, and now you can see the video. As you can see, build job is operated, and you can start the printer. And after starting the printer, you can see layer by layer the laser scans here the parts, and in the front type of the video, you can see the scanning of the support structure, as shown here. This step took several hours, and is really worked layer by layer. After the whole complete print process, you get a generated part within powder. You have to unpack them from the machine. Here you can see how the parts are released from the powder, just removed with a vacuum, very roughly, so we can then go on to a silicone depowder machine, where it was removed with vibrations. Here you can see how much powder is left in the support. After this, the first GOM scan was done on the build plate, and now we go to the wire EDM and cut off the parts from the build plate to release the parts and the supports. Here you can see the new technology I already told about. It's a trias blasting to remove the support structure on the titanium part. So you don't have to do it manually. You can do it with automatically a robot. After this step, the second GOM is following, and just for us to see if there is any deformation. After this, we teach our Hermle C22 machine, and all these tough parts was generated also in Siemens NX, the manufacturing application of Siemens. So you can see the finishing of the last features and the smooth surfaces. You also can see the clamping situation we have generated within the modeling. And also our Hermle machine is fully integrated, so we can do a simulation in Siemens. So now we will just change to the webcam for a quick picture of the part. Tom will hold it in the camera. Here you can see the part fully with support on it. And it's just wire EDM from the build plate. And then here you can see the ice blasted part, just a support removal. There is no finished surface on it. And after this step, you can see the clamping device and the finished product we can supply.
Okay, thank you, Kevin. So we go back to the presentation for the last step. So the last step is the comparison of the scanned parts with the nominal geometry. So what you see here on the right is the after printing scan that has been done. And we have 3 parts on the build plate. 1 was the undeformed configuration, 2 was support configuration A, and 3 was support configuration B. And so these are the deviations between what is scanned and what should be nominal geometry. So configuration 2 is we have a reduction of the support stiffness with the volume fraction. So the supports, again, they are not fully solid. They have a volume fraction, so every voxel calculates a volume fraction, and then we reduce the stiffness of this support with the volume fraction. Configuration 3 is similar. We also have a reduction of the stiffness, but there was a threshold value. So if the stiffness will not descend between below a minimum value. And on the next slide, we actually results after support removal. So again, configuration 1, 2, and 3. Configuration 1, which is the undeformed configuration, has large distortions on the supported surface, the large blue line, let's say. Configuration 3 has overall good deviations, except for 1 point where you have the light blue arrow. And configuration 2 has also good overall deviations, except for 1 point, which is the dark blue arrow. And so the question for us is which configuration is better? And the maximum deviation of configuration 2, the dark blue arrow, we know that actually this deviation was due to grinding. So with the ice blasting, the support had been pushed through the towards the surface. And with the grinding operation, a little bit too much material has been removed. And the same is not fully true for configuration 3. So also there has maybe been a little bit too much grinding at the bottom where you have the dark blue. But we also see that there is a larger deviation, which is red, at the top of the same part. So that means that this actually is due to a difference in the modeling of the support structure. And it's only configuration 2 where the deviations stay below 0.2 millimeter. And this is not the case for configuration 3. So the stiffness modeling of configuration 2, we judged it as the better one as compared to configuration 3. And this one is where all the deviations after compensation at printing are below 0.2 millimeter. And that brings us to the conclusions of the presentation. Mike?
Okay, so in terms of conclusion, we have a unified associative platform for additive manufacturing. We have a single software environment for managing the entire additive manufacturing workflow. We provide simulation and compensation. We can simulate the distortion of the part, including supports, and create compensated build plate. We provide a direct integration with TRUMPF. We have a seamless communication between Siemens NX and TRUMPF printers. Toolcraft provides printing and post-processing. As we've already seen, Toolcraft displays the full process chain in one software, less effort in handling data, and much lower risk of errors. And Toolcraft provides scannings and comparison. Different support modeling choices are tested, and total deviation was found below millimeters.
Thank you very much, Mike. So I think we can now go back to the camera mode. So I think now we can go to the, well, back to you, Caroline, and then see if there are questions for us to answer.
Perfect. Thank you so much, the 3 of you. Thank you for this great presentation. Just let me remind you that we have now 20 minutes for some Q&A, some question and answer from our speakers. So you can type your question. You have the Q&A box. Don't hesitate to type your question there. Also, reminder about the additional content available to you today through this webinar and also as an on-demand. So don't hesitate. Thank you for your reaction. You can keep say thank you to our presenter today using the emojis. Thank you for them. All right, so if you are ready, we do have a first question from Clément. So it reads in the Q&A, it reads, how is the improvement of the compensated model as compared to the original quantified in the printed product by post-print scanning and total delta per surface from nominal design intent? I don't know if you can see this.
Will you answer that, Kevin?
I can try, yeah.
And then if you also want to provide, complete feedback or contact Clément also offline, we can do that as well. Just if you have few info, and then I will go on with the other question. Thank you.
Yeah, the big value of the simulation part here at Toolcraft side or any other manufacturing is you have not to do many dry runs for a part. You can just simulate a part and got a perfect part within the tolerances.
Yeah, it is how it compares. So if you would not compensate, you will have a deviation.
Yeah, it depends on the shape of the part. Is there a really thick part? There's not so much deformation, but is there any thin parts or just thin layers or walls? It can cause this in crashes of the machine when the part stands up against the recoder, or really in a deformation up to 3 or 5 millimeters.
And in this case, also only with the configuration 2 was the overall, the maximum deviation was below 0.2 millimeter. And for the undeformed, it was above also for configuration 2.
Perfect. Let me see another question we have. So it reads, is the calibration only depending on the material, or does it also depend on the printer?
Okay, yes. So the calibration with inherent strain methods, you have to do them, it's a combination. So it's the material on the printer, and it's really the process parameter set. So you have the printer, you have a certain process parameter set. With the material, you have to do the calibration. So it's not that you can do a calibration for a material or for a printer. It is a combination of both.
Perfect. Thank you, Tom. Let me see another question. So what is the advantage of having direct integration with TRUMPF?
Well, there are several advantages. The first advantage, it will be direct communication between Siemens NX and the printer. This eliminates the needs of any intermediate file formats. Another advantage, it will be the streamlined process. That means users can manage the entire workflow from design to printing within a single software environment. And the third advantage is access to printer-specific settings. That means printer-specific build strategies and parameters that will ensure that the parts are printed with the optimal configuration for each machine.
We do have another question, this time from Sebastian. With which machine manufacturer you are working now, and is in your database, and is it possible to implement the software into every machine?
We have direct integration with all major OEMs: EOS, Renishaw, HP, Archiam, SLM Solutions, TRUMPF, Reichenbacher, and we are already working at the new integration for Farsoon. And in principle, we we provide a scalable framework for adding in the future additional integration. We have our Siemens Build Processor that is an open standard for adding additional integration. So basically, Siemens Build Processor will provide an output in a neutral Siemens format, and after the Siemens format, we can use Python post to convert the neutral Siemens format into OEM-specific printer output. This Python post processor can be delivered and can be provided independent of the standard release cycle.
Thank you, Mike. Another question, this time from Thierry. What is your best advice for students, newcomer interested in 3D print? DIY.
Maybe the best advice is just to get in touch with the topic. Maybe look for a chance to visit a company like TwoCraft. Maybe you can have a look in the manufacturing and just get in touch with the topic.
Perfect.
I think LPBF is nothing for DIY. It's too expensive, it's too dangerous.
Perfect, thank you, Kevin. Maybe also a question from you, Kevin. Which type of service does TwoCraft offer?
TwoCraft has a wide range of products. We offer high quality manufacturing part and also additive manufacturing part. We offer different materials like titanium, aluminium, Inconel, Highness in LPBF, and we also do DED. Furthermore, since 2019, we do consulting with our new brand Ambitious. So we do trainees for newcomer or students, something like that, just to get in touch with the topic. And also we do a VR training. We are now in our innovation area here, and you can really do VR training for additive.
Perfect. Thank you, Kevin. Maybe a last question. Will these products be available in the cloud as well?
For the simulation, at the moment, there are, well, it's not in the roadmap to, it will happen one day, but at the moment, it's not on the roadmap for the simulation side. I do not know for FixPlane.
For FixPlane, we are already working at providing our application in a scalable model within the cloud solution.
Perfect. All right. I think it's time to wrap up. If you have any final question, anything you need, maybe additional material, so do not hesitate to contact us. You have right now my contact details, so caroline.maitre@siemens.com. I also highlighted the box where you will find complete details and contact details for our speakers if you would like to connect with them after this webinar. Also a reminder that this session is being recorded. So you will receive a follow-up email later today containing the link of the recording of this session if you would like to share with your colleagues to watch it again.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.